This is Siddharth from Alphabet Learning, and we are going to start our complete beginners level, which is a 5 hours program on artificial intelligence. I hereby welcome you again for this 5 hours program, which will be starting from very basic scratch and will be moving on to the intermediate level, so that you can just know about what is an artificial intelligence and how it works on. So moving on, we'll just start off with our course overview. So first, we'll start off with what is an AI. Okay, so what is a AI really depends on, and why, where AI is used most, and what is the scope of AI. So moving on, next we'll just start with the beginners AI skill, and we'll make you to reach the expert level AI skills. Okay, so moving further, we'll just introduce about code templates, where you can just move on your idea or conceptual things to an AI oriented skill. Okay, so next we'll go on with the deep Q learnings, and further we'll be moving on deep convolutional Q learnings, and then at final we'll start up with A3C. Okay, so many people who attends this course might not aware what is meant by artificial intelligence. Right? So for them, I'm just saying what is meant by artificial intelligence is, suppose consider things like you and your machine are together working in an environment, right? So if your machine is given an operation like go to this place, means it will just direct to that place. It won't think like, okay, obstacle is coming, we should stop, we obstacle this is doing, I should do this. At the presence of mind, it don't have, it just follow the instructions blindly, right? So what scientists think is like, we should give the machines, even in particular robots, to have some brain, or to have some thinking capacity as that of an human. So what they did is they try to develop a thinking ability, like something like an intelligence of a human. So since they try to replicate that in the term of artificially, they are bringing out something which is equivalent to the human thinking. They call this as artificial intelligence. Okay, so the basic things we'll be covering in this also as something like a hands-on. Once we are done with our learning, we'll be looking on with a virtual self-driving car. Okay, so moving on, we'll just develop a human robot games, in particular a board game. We can just develop something like a user and then robot, or a user and then something like a machine will be playing, right? So this is not something new, right? Even if you download some games, yeah, like something like in your mobile, if you download a game something like chess or a monopoly, right? So if you give a single player mode, obviously the computer is playing, right? Yes. So this is the basic concept of this artificial intelligence. Okay, so moving further, the course levels. So let me just brief you about the course levels. So this this is where we are currently in. So this is a 5 hours program. So we are at the level 1. So in this level 1, we'll be starting with very basic scratch, and we'll give a appropriate idea on how artificial intelligence works and where and all artificial intelligence is involved. So following that, we have our level 2 program, which is a 10 hours program, where we'll start to build our AI skill set from our learnings which have been done in the level 1. Post that, we'll have our level 3, which is obviously of 10 hours, where we'll be introduced to real world applications and real world buildings of course, uh, something like a self-driving car, something like a a much intelligent robot. We can just build something like that. Okay, So what will be the benefit upon starting this course, right? So upon completion of this course, you'll be getting a globally recognized ISO course completion certificate on the domain artificial intelligence, right? Without wasting much time, just move on to the slide. The first question arises, right? The first question arises, why is AI, right? Why is AI? The first question is, why is AI, right? Well, we have all heard about the applications of artificial intelligence that are popping up around us, which includes, as I said, it's a self-driving cars, a medicinal background, a heavy machinery, and much more on, right? The service list of AI just keep on. We can't imagine. It's like tremendous service it does. So you people might ask why it is not. We should adopt it 10 years ago or 10 years later. The question or the answer for the question is well and good here, right? Which is called the Moore's law. Okay, it is originally identified in 1965 or more. What it says is the power of an average computer in like a in very simple terms, the power of an average computer which you can buy for $1,000 will double every 18 to 24 months. You can imagine that. So what it does, I will repeat, uh, the power of the average computer which you buy for $1,000 will double itself in every 18 to 24 months. And that's been as easy as a law that helps and through good times and bad. See, war and peace and the recreation depression, nothing stopped this. Even if something like a pandemic time like this, nothing stopped this. This count like it get doubles, right? In 18 or 24 months, it gets doubles, right? So we can see that here. Uh, we have already surpassed the brain of an insect for another computer was going for $1,000. Okay. We are sitting at about the speed of the processing of the brain of a rat by 2025 will be at the time of a human. You can see it, okay? You at the age of 2025 or the year of 2025, you can obviously note how it exponentially increases. So you can see it's tremendously growing. It's exponentially growing when we just move on to the years. As I said, every 18 to 24 months, the average something like it get doubles. The knowledge get doubles. So this is a great time to be in an artificial televisions. Something it sounds great, right? It's not a something like a technology or something like that. It's like a television. You can project everything. So we just call it as artificial television. Okay. In fact, indeed, it's just going to be doubling the power. Is going to be doubling every time or every 3 minutes. Can you imagine? Every 3 minutes, it's gonna multiply itself. No one can imagine that, right? So, yeah, this is, you can see. So, what's my favorite example or related to games like chess and more on that, okay? So, in 1997, DeepMind was the first computer to beat Gary Kasparov in chess. What? A computer? I'm just saying, a computer have won a man named Gary Kasparov, which was a what to say in 1997, which is a big event across the world. Indeed, it was a huge thing. It was like one of the most broadcasted chess game on the planet ever. Okay, So that was likely considered it an impossible feat right now. As we can see in our phones, you can install a chess which no human player will be ever, right? Because obviously humans, computers are better than humans. I mean, in the work they do, right? So now you just can't beat computer. Something like it is the hardest thing, right? Even if you are in a work field, even if you are playing, it's just quite hard, right? Even they think better than us, right? So I'll just move on to the next thing. Okay, a computer. This was happened 4 year back. So in 2016, a computer won against the not a human, not just a player. He's 18 times world champion. Can you imagine that? So a computer won a 18-time world champion of a game of Go. Lisa Ideal again considered an impossible feat even at the start of the match. It was considered to have to be impossible that it's going to happen 10 years from then, but it happened, right? So they were thinking, okay, we can just build a computer. A computer era will be after some 10 to 20 years, but it was happened in 2016. By the way, if you didn't like find out a bit more about games, it's very interesting. Okay, it's got 40 media players, and the 1,000-year-old games were popular in China and Japan, and it's much more complex than chess. You can imagine that it's much more complex than a chess, and it's would just there are many possible combinations. The game is obviously full of combinations. So again, something I would consider impossible is happening, and it's happening now, and much earlier than its time, right? We just expect something like every 18 to 24 months, but it happened in something like 2016. So that's what you will see from this course, and you will see that we are using games to train artificial intelligence, and why we are doing that. Because games are confident in environment where we can see we can beat a game using an artificial intelligence, then we can use the same principle to apply to business itself, right? So even not only I just said before, not only games, we can just apply the same principle to the business. Yeah, they did. Sorry, they did. And that's what exactly same thing that the team at Google DeepMind, who created an AI which went to these stages. They exactly what they did is they applied artificial intelligence to Google's one of the Google's warehouse to control the air cooling system. And what they found is that electricity bill is a consumption which has consumed, right, for doing that air cooling to that warehouse. It was reduced to the 40 percentage on their regular electricity bill. This was insane, right? You can just obviously, if you want to get more idea, you can just I have mentioned the source, you can just navigate to that, and you can just see that, right? So we are at the final stage of the topic, why AI. Okay, so I have described here waitby.com, okay, where you can just see it is an actually amazing blog by Tim Urban. Okay, this is how he just described the situation where we are currently in. Okay, this is us, and this is the human progress, and with respect to time we just see some gradual increase, right? We just see some gradual increase. At the starting it was like knowledge was this, it was keep on increasing, right? So when artificial intelligence comes into this place, oof, the steep was too high. So we are going to experience this. It's not too way long. So we might be experience this steep. In to be very honest, we have started to experience this steep. So in future it will be a very steep, not like this, not like your parents or your grandparents were did. Okay, so you have to be surviving in the next or the upcoming years by trending you by changing yourself according to the growth of human progresses, right? So without wasting much time, we can just proceed. Okay, we can just go on to the plan of attack. So what is meant by plan of attack? Okay, we are going to discuss the plan of attack for the selection we have made about to learn this topics. Okay, and we got quite a few tutorials, so I just think it's good idea for us to quickly go through them to understand what to expect in the upcoming session. So here we go. Okay, here we go. So what we will be learning in this session? The first thing is we'll talk about the reinforcement learning, what actually does, and what is the philosophy behind reinforcement learning, and is how a reinforcement learning actually can be seen in real life, and how it relates to the things that we observe in a real life, which are actually things that we do ourselves indeed. Okay, but they don't talk about something irrelevant to this. Okay, so what next? It's a Bellman equation, right? So Bellman equation is a very fundamental concept underpinning everything or a lot of things that are happening, and for reinforcement learning, especially in the space of Q learning, and what we are going to discuss in the session of the course and in the following sessions. Okay, then we'll talk about the plan, and the plan that the row are what to say the artificial comes up with the in order to navigate inside certain environments. We'll see that how that comes together very quickly, but it will be, I'm just telling you that it will be quite interesting. Okay, so then we'll talk about MDP. What is meant by MDP? Okay, so MDP is Markov decision progress. Okay, it's something related to the decision predicting of what to say decision making things. So if at all a thing is there, if at all what to say if at all system is there, what kind of decision it was supposed to take while it was under some circumstances, right? So these are the things. And then moving on, next we'll be studying about policy versus plan. What is mean by a policy, what is mean by a plan, what is the difference between those? We'll be seeing that. Okay, then moving that, what we'll be seeing is adding a living penalty. So living penalty, that term describes that. So depending upon what environment we are going to add a different technique. Suppose in a driverless car, you'll be sensing different things. It will be a different, totally different way if you are seeing something about a game, board game, right? So depending upon the environment, we'll be adding some living penalties. And Q learning intuition, which is something like what and all things to be considered or what are all to be interpreted for that thing. And the temporal differences and the Q learning visualization, the entire visualization will be done. Okay, so moving across, we'll be first starting with, see, I'm just making you clear whatever we see, the terms we see might not be familiar with you people. Okay, so I just gave you a hint like what we are going to study. Don't worry if you think like, sorry, I can't know about this. Is I'm in the right place to learn about this? Yes, you are. So I just gave you the topics. So we will be seeing individual topics one by one from the very basics so that you will understand that. Okay, so the first thing is, what is reinforcement learning? Okay, so uh, we will just talk about this reinforcement learning. It is a very important story because it will underpin everything else is going to be happen in this course. Okay, so the reinforcement learning is the key word for an artificial intelligence. So without wasting much time, let's start there. Okay, so here you can find a little maze, and this maze is our representation of an environment. Okay, I'm just coming with an example. Okay, so we have a maze here, something like you know, right, maze. So this is a representation of the environment, but we are referring in an artificial environment, right? So this is an example of an environment. That's what we are. Okay, so going to be dealing with this course, we are going to be dealing with certain environments in our artificial intelligence, which is going to be performing, it's going to be taking action, it's going to be looking to beat in this going, she will be looking to win this environment, right? So we got an agent. Okay, so the maze is the environment and we have an agent. The agent is the artificial intelligence. Okay, the agent referred here is the artificial intelligence. The agent is the person, or that's the mind, that's going to navigate this environment and learnings to form a feedback that their mind are going to be given in order to perform certain actions. Okay, suppose consider to be, I'm just relating with a driverless car. So driverless car means what a driver actually, in a driver, what he will do, he'll just drive the car, he'll be just aware what and all is obstacle is coming, or he want to take a turn, or he want to apply brake, or he want to accelerate, he'll be doing that, right? In a driverless car, these things should be should be replaced by a machine, right? By the car itself. So what should be done? What should be done? So action, okay, action should be given to that. From the agent to the environment, certain action should be given. Okay, for that action, we'll be getting a state or a reward. What I said is, as a result, the state in which is it in will change, so it might be further or closer or more to the actual output. Getting that? It might have short of other parameters that describe its state and other those parameters. Just as of now, leave about that. So the state is going to change because of action that takes, and it will also get rewards based on the action. So we are giving some action. So in that environment, we are going to give some action. For that, we are going to get a reward. See, we are going to give some action. For that, we are going to get some reward. So here comes the next thing. The state is going to change because of the whatever action we are going to give. Based on that, we will be getting the reward. Okay. So suppose consider to be a wall is coming in front of my car. My action, if my action is applying brake, I'll get a separate reward. If I just accelerate still, I'll get accident, which is another reward. Okay, so every time it takes an action, the state will change, and it will get a different reward. Now bear in mind, sometimes it might happen that it won't change the state, the action won't change a state. Okay, even though the action changes, the state won't change. Okay, so but nevertheless, the agent's going to keep doing that, what going to be taking action, cheating that exact state. Okay, getting rewards, changing action, taking action, changing the state, and getting rewards. Okay, and by doing the process, it's going to be learning about what was going to exploring the environment, understanding what actions lead to good rewards and favorable state, and what action the two rewards and an unfortunate state. Okay, this is very simplistic representation, and for a global problem we can just implement an artificial inside that, right? So if you think about it, environment actually, which doesn't have to be just a maze. It's not just about getting out of a maze or finding a treasure in a maze. It's not like that. An environment can be pretty much anything in life. So imagine you are waking up in the morning and cooking an omelette. So in order to make that omelette, you need to go through certain steps, which you need to do, something like to get the salt, get the eggs, get the frying pan, which is to fire on, and so on. And it does sound like a routine, mundane things, right? But it's become a routine because you have done it so many times in your life. But in reality, it's an environment where you are performing certain action. You are taking that, you are putting on the fire, on putting on the frying pan on the fire. You are putting all the eggs into the frying pan, and you put some salt on the eggs, and you are turning over, and so on. You are doing many things, right? So you can see there are certain things, certain actions which are taking in certain state, and those actions, right, which leads to certain other states and sometimes some rewards. What is the reward here? So if our action was quite good, so we'll get a good omelette. If it is somewhere it was wrong, we'll get an omelette, but we can't taste that, right? So for instance, you when you put the fire on and you wait, you take an action of waiting here, right? So what you are doing, you did an action, and also in another action you are going to wait, wait too long. And then what you do is you put the eggs into the frying pan, and then the rewards are going to be very negative. It's all going to burn. On the other hand, if you do all the correct action in the correct time, so it's very important to understand that the action should be taken at a correct point in the time. So for instance, putting the salt in the frying pan before you put the eggs, it might not be the best idea. You might want to take that action of putting the salt into the frying pan after the eggs are in there. So there is a different state, right? So first state we just put salt and then egg, which is as action, and the second thing is we put the salt into the frying pan after the eggs are been there. So there are two different states, right? So it is important to remember that too. At the same time, so if you take all the correct action in the correct order in the current stage, your final reward could be that you get an omelette which you can eat, right? So that's a very basic activity in your life. But if you think about it, which is actually an environment, and you are the agent going through this environment and performing a task which you don't really need to learn anything because you already know it pretty well, right? So but at the same time, you could learn, maybe you could learn how to make a better omelette, or especially if your first omelette that you are making, you are probably going to get screwed it up, right? In the same time, you learn about that because you will understand what action leads towards states and routes and anything else in your life. For instance, even trading on the stock market, and buying, selling, and getting certain feedbacks, right, from the market, in the sense of returns, right? Now, either it may be a positive or a negative return. There it is something like the stock market, the marketplace is your environment. Your action is like when you are going to withdraw it, when you are going to your money invest there, that is your action. So the profit or the loss which you get is the reward, right? So that's also an environment, that too, right? So as I said before, driving a car is also an environment where you can turn the steering wheel, you can accelerate, you can brake, and so on, and you are getting feedback from the environment. And one of those feedback is the policeman giving you a speeding fine if you are going about some mentioned speed on a certain highway, right? And therefore from there you will learn that nothing should be done because it leads to a negative reward. so I paid a fine, so that should not be done. So what it will automatically reflect, so it is a negative feedback and it will be something like it won't be repeated again. The machine will confirm that it won't be repeated again. Okay, so rewards don't have to be just at the end of the process, they can be throughout the journey, throughout the process. So these are some of the examples of this what is mean by agent, what is mean by environment, what is mean by an action, on giving an action, certain action by an agent to the environment, what we will get. Okay, so when we move on, and in the terms of a simplest way how to think of reinforcement learning is like training a dog. Okay, when you train the dog you want to give certain commands, and if it obeys those commands, then you give it a reach, you give it a like a biscuit or something. If it does something like if you ask it to sit, or if you ask it to roll or something like that, right? So it's a if you tell that it's a bad dog, or if you don't give it a treat, and throughout the process it learns whatever certain commands or what it needs to do, what action it needs to take in certain states, and the states are commands that you are going to give it, and based on that it will get some certain rewards of the course in the world of AI too. Okay, the next thing, see, it's not an what to say, basically you just keep in only one thing, agent is going to give an action. For that either the reward will be positive feedback or negative feedback. So positive means +1 and negative means -1, right? So if you get a negative feedback, the machine automatically restricts that action and it won't repeat that again. Okay, it's not that complex. You don't have to give the treat, you don't have to like a bag of biscuits with every time you just want to, what to say, you don't want to give it as a +1 or a minus, right? Once, see, it's a huge advantage that in the world of AI we have created these AIs ourselves. Okay, so the rewards that we are going to give them, if you think wow this is really cool rewards are giving to them, they don't actually exist. They are just a minus and one plus. So it's not like a dog, it's not like a omelette, right? So it's just like a minus and a plus sign. So your machine gonna do something and you are gonna give a plus or minus, so it will just get the feedback of its own. So it's not non-existence at all, it's an imaginary stuff. But all the same time it leads to a greater result, as we can create these amazing things, these amazing artificial intelligence, as by this amazing artificial intelligence, by just providing rewards, we don't really exist, right? So plus and minus one doesn't cost anything, but at the same time it releases the results. So very familiar to, which is very familiar to the real world. Okay, and for examples, something like dogs, but there the rewards are digital and just numbers, right? You just know about dogs, right? So we have a reward something like digitals and numbers, right? So it's something like that. Okay, so yeah, and with that in that mind, we can just talk about robot dogs. Actually, I love this example, something like this is just around in the picture, not especially not necessarily in the indeed that exactly a robot dog, what is do, that is trained to a reinforcement learning, right? Some of the robot dogs, especially the older ones, you would have an algorithm inside that, right? Even every robot, right, not only a robot dog does have, every other things have an algorithm inside that, right? Similarly the robot dogs have some algorithm, and this will be usually a good example of the difference between pre-programmed agents and a reinforcement learning agent. So that you could have a robot dog which have pre-programmed to how to walk, some certain commands, how to walk, how to bark, everything we can say, right? So in the algorithm behind the dog is the software will say, okay, in order to walk you need to move, if you want to move leg side, to move if you want to move right side, right? Leg forward, then you
your backward leg forward, and then repeat the action. Something like if you want to move right side, make something like right side legs to be back and the front side legs to be front, so that the entire robot turns right. Okay, these are something like a walking function inside this dog. And then it might have you like know how to sit, how to stand, things like that, right? So we have everything predefined. Whereas in a robot dog that is trained, that is being trained, so you're not going to program it. You're going not going to sit and write, okay, turn the motor something like this, turn the motor something like this, if this is the command, do this, right? Here the robot dog is gonna train. How your dog, how your puppy is going to train, the same way it's gonna train. That's the word, the reinforcement training. Okay, that robot dog that is trained to reinforcement learning, what happens in you, which doesn't pre-program it. Okay, this is the key concept to everything here, that you have no algorithm inside the hard coded or anything inside the dog. Instead what you have is, we'll be discussing in that future classes, which is indeed, you know, right, it's artificial intelligence, right? You have this reinforcement learning algorithm which is told that, okay, so the goal is from to get from where you are now, not knowing anything, to the end of the room, for an example. Okay, so something like that, you close, you just visit a new place, your eyes has been closed, you'll just go for some, you'll just what to say, you'll just touch that everything, and you'll just come to know, like, okay, this and all, here it is there, it is there, you'll just try to learn, right? So here it is there, okay, I just not move there, I just go there. So you'll be keep on learning something, right? So the same things happens here. Okay, so what we can do, if the dog was without any algorithm, it just was, we'll just give a command, walk. So what it does, it just goes like a list of action you can take, and your rewards are every time you can step forward. You get a plus on every time you fall over, and you will get a -1, and that's all there is to it. Okay, and then it just leave the dog and let it figure out down it by its own. We are not going to get involved in that. Okay, so the dog tries to stand up, it falls, then it realizes that, okay, I should not do the action that let me falling, because every time I fall I get a -1, which is not good for me then. So does the action that help him stand up, and it figures out experimentally. It does experiments. It does experiments. It just do that. It will do this. For every action, it will be a feedback. Whether it's a positive feedback, it is a negative feedback. It will just learn from that. Okay. Then it tries to figure out that it can make a step forward by moving it right front foot, and it will just do that. So after doing a set of things, it will do that, and then it says, okay, cool, so it's now learned that it should do more than this and less than that. It will come to this something like, front leg is going too far and the back leg is something like a short, it will just fall, negative feedback. Okay, just eliminate that. Next combination. At certain things, when it get positive feedback, it will just store, okay, fine, this is good, this is cool, just store this. When I was instructed to walk, just do this, right? And throughout this learning process, it quickly, very quickly understand how it can walk. Okay, and those dogs that figured out on their own can actually sometimes walk better than a real dog does. Okay, a real dog means, I'm not saying the dogs which gonna walk in street. I'm just saying that the dogs that are pre-programmed, because really pre-programmed things, we look at the real life dogs, or we use our own imagination how to do it, wherever the reinforcement learning dogs can optimize things on its own. And because in AI, sometimes it can be get a even more better result than human, or the human range of thinking. And that's how they can train these robots. The same robot dog to train something to play a scozer, because simply the whole approach is different, right? and it's not something that probably a normal dog have been trained to do or have ever done in the process of evolution, right? Wherever a reinforcement learning robot can very easily understand how to play the squazer, as long as you tell them what is the rewards or what the goal or what the possible action they can take. So that is how reinforcement learning works. In general, that is a quick overview of reinforcement learning. Okay, so I hope that got very excited about what we are going to see next, because it's a completely different world, right? So till now, if you see something like a dog, if it is something like a dog, you can refer to a puppy. And if you are a dog robot, means what you'll be thinking, as like in a movie, you'll just think we want to program something, we want to say everything. But now we are going to enter in a different world where you'll be just doing some basic things. Then as like a kid, as like something a newborn kid, where it will be starting to learn by seeing everything, doing something, the same things the robot gonna do. The artificially inserted intelligence gonna work. Okay, so this is very different, and we are going to be talking more about that. In the meanwhile, you got some what to say, you got some additional uh, reading that for you, if you like to have some supporting materials. Okay, so here are a great article which you can look into, right? So it's called Simple Reinforcement Learning with TensorFlow. It's got 10 part actually. The link is here. You will find the full link on this the slide. So in the course of resources by Arthur Giuliani in 2016 article, and you can follow along this course and also get some additional information about the article. But bear in mind that the article is tend to flow, whereas in the course we are going to use PyTorch. So different implementation, but implantations. But at the same time, you might pick up few things here and there that might supplement your learnings that we are going to be doing in this course. So great article. Follow you. This follows. Okay, in that if you are considering, do follow that. Still, in case, check out the that first part and see if you like it. See if you like to read it a bit more. Right, that's not a big deal. Right. So and then we have got a specific to this tutorial, a border enforcement learning. There is a paper by Richard Sutton which is called reinforcement learning. One introduction is in the 1998 paper, are quite old, but at the same time you can learn a bit about reinforcement learning. Some of the examples like that omelette example are the examples where the reinforcement learning can be applied, and just a general overview of learning in reinforcement learning. If you are looking for some additional reading, and on the note where we are going to wrap up this tutorial. Okay, and then what next? We just saw about uh, reinforcement learning, right? So we'll move on to the Bellman equation. Can anyone tell that what is that Bellman equation does? Yeah, so now we'll move on to the Bellman equation. So let me just move on to the concepts before explaining to the equation. I'll just explain the concepts or the variables involved in that. Okay, so S describes the state, and A describes the action of the agent, and then R describes the reward, and then gamma describes the discount factor. Okay, so I'll just describe you once we just go into the equation. Okay, so this was the term the Bellman equation was termed by the Richard Ernest Bellman for especially for this to predict the way, to predict the possible way. Okay, so I'll just start with a simple example. Okay, so here we just have, right, here we just have a agent and we have two states, right? So I have a positive state and a negative state. How to say positive feedback and negative feedback? We just So are the things, right? So positive means a plus symbol, and a negative feedback means minus symbol, right? So for a negative or to negative or negative feedback, we can just give r is equal to -1, which is a reward is -1. And for a positive feedback, reward should be +1. So what I should do now? So this agent to navigate to this square to get a positive reward, right? So what is the possibility of the this agent? He can just move to the right, and then again right, and then he can just go to left, and then same position. He can go up like this, and then he can go right, okay, and he can just go back to the state, and he will get the reward to be +1, which is a positive reward. Now we just directed, right? It was like here, and just we directed move up, and then up, and then right, and then right, and one more right to reach that feedback, sorry, positive feedback, right, to get a reward. Okay, now I should ask, I should say, okay, consider if my robot is doing a work. If I say it is a positive feedback, the robot will do again that. If it is a negative feedback, it won't do that, it eliminates that way, right? So what I should do, that it was moving from this place, from this place, then this, then this, then this, then this, then this, right? So I should increase that, moving that way. So what I did, so I should do this is as a positive feedback, so my robot does that, right? So I'll just write reward or the value to be 1. So after that, what I did, it was previously before this was this, its state was this, right? So I just said v is equal to y 1 here also. So I give up a reward. Same way I'll reward here, here, and here. Okay. Now when my robot is in here, it will get a positive there. Okay, go, 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 and then reward it gets here. Now the confusion comes when my robot is navigating from this, then this, and this. Suppose consider to be, if it is here, it will get a confusion. Here also v is equal to 1, here also v is equal to 1, where I want to navigate. Even if crosses here, it will get a confusion like whether I want to move up or down, because both the values are 1. I am confused where I want to go, where I want to move my next, in which direction I want to move my next move. So this method fails. Okay, this method fails because everywhere same value. So the at the middle, the robot gets, or the navigation gets failed. So what comes next? How to solve this? So to solve this, we got the Bellman equation. Okay, so what if you just explode Bellman equation? It is like the value of the state is equal to maximum action. When maximum action is given, what was the state and state's reward? Okay, so for a given state, what was the maximum action was given, for that what is the state and reward, plus reward factor times the gamma. I'll just come over that in further class, further sessions. As of now, we just deal with that. This is a reward factor. Okay, so into previous value of the state, so preceding value of the state. Okay, now using this, see, value of the state is given by the maximum value of action which corresponding to the state and its reward, plus gamma times of previous state's value, right? Consider now, if I go to this place, I'll get a reward, so I should fill this. Now it is the first box, so previously it don't have anything, this term becomes 0, so the maximum value is 1. Okay, now I move to the next column, next square. Now what is the maximum value? What is the maximum value? what is the maximum value here? For that, I just want to use what is the maximum action I can give, what is the maximum state I am getting or that reward, plus factor times of previous values state, right? Suppose I'll get my reward factor to be 0.9. Okay, now if I move that, I'll get 0.9. Okay, so I have this factor gets eliminated. Okay, so see this plus 0.9 times of previous factor is 1. So 0.9 times of 1 is 0.9. The same way if I go before, this factor is eliminated, and then gamma times of previous factor 0.9 into 0.9, this is 0.81. Now similarly I'll just fill that. Now when my agent is here, okay, it will just go for the maximum value. So 0.66, 0.73, it will move here. Now it will be here, it have two choices here or here, so it will just compare these two value. This is bigger, so this moves here up. If it is here, it will just compare these two possible ways. This is higher, so it will move here. So if it is this case higher, this will move this to here, right? Now, okay, now what should be done here? Either I want to do with the same equation something like 0.6 gamma times of 0.6 I should do. No, right? So if this is the place, my easiest way is going to this side and this, right? So I should calculate from, I have two possible ways. If I go like this, it is a very longest way. If I go like this, it is a very shortest way, right? So I want to start with calculating here. Here means I have three values. So I can go here, or else I can fall in the pit, or else I can just move here, right? So in the here, I'll just take from the state 0.9 using Bellman equation. Now this set. Here I have three possible ways. So here to here I just apply 0.9 times of 0.9, I get 0.81. Same way if I just choose here, like this I am going, right? So 0.81 times of this. So when I fill that, 0.73. The same time here, if I am here, I cannot go like this because it is a negative feedback. So I should go like this, and like this. So preceding value 0.81. So 0.81 times of 0.9 is 0.73. Okay, if my agent is in this position, it will compare. It has two possible ways, this or this. Compares, it will just take the largest value, it will go here. Compares these two, it just goes here. Same way if it is here, it compares this and this. This is much better, so it will go like this. Instead of following a big route, it will just follow here. Then when it is here, it will just compare this and this. Okay, this is better, this it will go here. This will compare this and this, it will better, go here, go here. This and this, it will compare, go here. Okay, I have an additional reading about it, the Bellman equation. You have an article called The Theory of Dynamic Programming, which was written by Richard Bellman in 1984, where I have attached the link, so you can find that link. So if you want more knowledge about that Bellman equation, you can just navigate to the link and you can find that. Okay, so the rest of part will just continue with the next video. Okay, thank you.